everyone, and welcome to PathWave Design 2022 High-Speed Digital Launch Event. My name is Anna McCowan. I'm a marketing manager at Keysight Technologies, and I will be your host for today's webinar. So let's move on to today's agenda. We have a great lineup today. Our first speaker is Tom Lillig, who is the General Manager of PathWave Software Solutions here at Keysight Technologies. Next, Perry Keller will answer the question, where is DDR memory heading next? Then I'm delighted to welcome Ben Dannon from Northrop Grumman, who will share a rigorous design analysis of a DDR4 DIMM base system. Finally, Keysight's own Stephen Slater will provide an exclusive look at the latest release of PathWave ADS for next-generation memory designs. So with that, I am pleased to welcome Tom Lillig. Tom, you now have the floor.
Hi, my name is Tom Lillig, General Manager of Keysight's PathWave Software Solutions team. Welcome to the PathWave 2022 High-Speed Digital Design webinar. We all know that electronics design continues to get more and more complex in several different ways. First, designs are ever increasing the number of transistors, density, and overall size. That alone is a challenge, but what exacerbates the problem is that signal rates are getting faster. More and more digital and power signals are looking like RF signals as they radiate, cross-couple, and interfere with each other. Also, as circuits get faster and more dense, thermal issues have a bigger impact on the circuit performance. We used to be able to solve these problems in isolation. We could design the circuit, then solve electromagnetic problems, then solve thermal problems, and then solve power distribution problems, and we would pretty much do it in serial. Now, because of the higher density and coupling, we must solve these problems concurrently. What used to be isolated challenges are now more often interconnected problems. Simulating and modeling the circuit, EM, thermal, and signal integrity together is becoming more and more necessary over time. On the other hand, it's not practical to take your entire circuit board and run a 3D EM simulation on the whole thing. The simulation would take years to finish, and practically not all of your signals need to be modeled in that way. So the key questions become, which type of EM simulation should I use for various parts of my design? What's the best approach for setting up the ports? When and how should I combine my EM, circuit, and thermal simulations? How should I partition my circuit into manageable pieces? Well, the answer depends on the application. The good news is that the tools are evolving with greater intelligence and application awareness to help with these decisions, and even make some of these decisions automatically. This is part of an evolution in high-frequency EDA. Previously, different types of simulations were done by specialists. There are EM tools for EM engineers. There are thermal tools which are usually driven by thermal or mechanical engineers. There are RF circuit design tools driven by RF engineers, and the list goes on with power engineers, PCB engineers, etc. In many cases, we still need specialists. As a matter of fact, we'll certainly always need specialists. But the downside of this approach is that it's just too slow to get to market. There are too many silos of people doing the work, and because of the challenges mentioned on the previous slide, by doing everything serially, we end up with lower performance designs. As a result, we've seen the emergence of engineers who run multiple tools. RF engineers have learned how to use EM and thermal tools. Power engineers are needing to become EM experts because of high edge rates on switching power supplies, which are really causing circuits to blow up. High-speed digital engineers are becoming experts at signal and power integrity, etc. These engineers can create more optimized designs, but only if they can become experts in all of these different domains and learn how to use all of these different tools, which were really designed for specialists. Now the market is evolving to application-optimized tools. For example, Keysight has tools called SI and PI Pro. These are tools designed specifically for high-speed digital applications. They combine circuit design, EM simulation, and thermal simulation into a single tool. Not only does this make it easier for that high-speed digital engineer to use the tools, but perhaps more importantly, the tools enable the engineer to develop higher performance circuits and higher performance designs and more accurate simulations. because the tool knows that the circuit you're trying to design is a high-speed digital circuit. With that knowledge, the tool can make further optimizations for high-speed digital circuits, which don't apply to a power circuit or an RF circuit or a generic EM circuit. Similarly, we have a tool called PE Pro for high-speed power electronics engineers and RF Pro for RF engineers. Ultimately, this approach can provide the best performance with the shortest amount of simulation time and with the shortest learning curve to learn the tools. As I mentioned earlier, these application-optimized tools don't eliminate the need for specialists, but they do allow each design engineer to get much further along with their design. As a matter of fact, at Keysight, we also develop tools that are optimized for specialists, which use the same underlying simulation engines, common user interfaces, and common APIs. This makes it easier for various team members, specialists and generalists, RF, digital, and power engineers, to share their designs and their results among each other. I'll finish with an example, SI Pro. In this example, there are 8 channels of DDR. SI Pro has a tool called Rapid Scan, which calculates all of the impedances of each section of each trace. This can provide a quick step to check for common problems. The tool ensures that the signals that are supposed to be alike in impedance are indeed alike. It checks for issues in time alignment and generally ensures that the circuit was set up properly. Next, SI Pro has a tool called DDR Setup Wizard, which helps set up a circuit for EM simulation. By simply selecting the memory and controller, the tool automatically determines which nets are part of the memory bus, which components need to be included in the simulation, which plane should be part of the simulation, and the frequency plan. Next, EM simulation begins. Normally, a full 3D EM simulation would take an unreasonable amount of time for the circuit with this many nets. However, SI Pro, due to its application awareness, can provide things like mesh reductions. It can split the circuit into sections. It can decide when to do planar versus finite element electromagnetic analysis. These are steps an EM expert might be able to deploy based on their experience, but we're able to do that automatically with the tool. It's as if we're capturing an EM expert inside of the tool. That example was a large design, but it was also a real design. SI Pro takes advantage of parallel processing. The tool basically takes advantage of the fact that there are often multiple cores on a single machine. We can also take advantage of the fact that you can have multiple cores and CPUs across a cluster of machines. And we can further take advantage of the massive parallel computing power of the cloud. The example I'm showing here was with Seco, a leading developer of IoT solutions. They're using SI Pro in the cloud. This allows them to both provide very high performance and provide add-on scalability, or I should say on-demand scalability. They're able to ramp up and down the compute resources they need at any given time. By running high-performance computers in the cloud, they are able to reduce their simulation time from about 3 hours to about 30 minutes. But perhaps more importantly, the on-demand capability of the cloud has allowed Seco to do more simulations that they normally would not have done. They end up with higher confidence designs that are more likely to meet their requirements the very first time they produce their product. Next, you're going to hear from some of our experts who will talk in more detail about new challenges and solutions for high-speed digital design and simulation. So thank you and enjoy the webinar.
Hi, my name is Perry Keller. I represent Keysight within JEDEC as chair of the JC40.5 Memory Validation Committee, as well as on its board of directors. Today, I wanted to spend a few minutes to acquaint you with the technical road that JEDEC has taken to get to DDR5, as well as some of the follow-on considerations that might have to be taken into account to move beyond DDR5. So as the technology underlying DRAM changed from DDR1 all the way through to DDR5, and also going forward, the concept underlying the test, measurement, and design tools also had to keep pace. So this included things like probing, how one goes about probing signals, what kinds of test fixtures are used, what kinds of measurements are appropriate for measuring transmitted signals, for example, with the scope, or received signals with the BERT, or protocol and logic analysis, which are still required given the complexities of the DDR5 training sequences. New in memory is, in importance, is power management and power integrity because of these speeds. And then also, of course, the design modeling and design automation tools really had to evolve and adapt and incorporate new concepts in order to support especially for DDR5, the advanced technologies required. So to give you an idea of how these have changed over time, let's go back about 20 years to the beginning pre-DDR with low-speed digital interfaces, which you can still find in some of the flash memories. This is where fan-out and load capacitance, for instance, are really the key design parameters that you have to manage. With the introduction of DDR for about a dozen years, with DDR1, DDR2, DDR3, there was a big transition to high-speed digital design, which now is kind of old hat for everybody. But at the time, it was quite new. And the core of that was thinking in terms of interconnect as being a key part of the design that had to be managed, and that timing and signal integrity were really the key things that had to be understood and optimized. Setup and hold times, ring back, those kinds of things. That was a comfort zone for the industry for about a dozen years until DDR4 came out, when concepts like random and deterministic jitter and noise really became the centerpiece of the specification. Those were the key things that had to be managed for success. This also required changes in how the designs were done, verified, and validated and tested. And that was quite a transition for the industry to make. Now with DDR5, even those concepts are becoming less important and replaced by things like impulse response of the channel. The requirement for an equalizer, a decision feedback equalizer in DDR5, really requires that the specification be written in many ways in terms of what the impulse response of the channel is that the receiver has to be able to compensate for. And that pace is going to continue when looking at the next generations after DDR5. In fact, now with every generation, something new, something fundamentally new is coming up. And it's quite likely that the whole idea of NRZ signaling will have to be abandoned as the fundamental core of DRAM interfaces, going to things like PAM4 or perhaps even complex modulation. The key thing that makes this a challenge in memory, unlike other interfaces like, say, PCI Express or USB, which can think in terms of embedded clock high-speed serial, is that memory really is the last traditional parallel bus because of the requirements for low latency and a huge amount of signal throughput. So it has an explicit full-rate clock. It's wide. It's single-ended to be economical on pins. And it's bidirectional, and it's also bursty. So the short burst lengths on DDR5, the shortest ones are actually 16 bits long, which is very short compared to high-speed serial. This is something that's especially difficult because it has to be able to work in a DRAM process, which is not optimized for logic. It's optimized to build lots of capacitors. So it's very slow and unfriendly for logic implementations. These high-speed interfaces can only be done at the I/O with highly specialized layouts and designs. And all the smarts really need to belong in the memory controller. So if you were to compare, for instance, the front-end interface to DDR, compared to that for a, quote, high-speed serial interface like serial ATA or PCI Express, memory is simplicity itself. Instead of having a PLL that can multiply a low-speed reference clock and then a clock and data recovery circuit, along with a variety of equalizers in order to open the eye up for that first sampling flip-flop. Memory really just has that first sampling flip-flop, and it's up to the controller to make sure that the eye is open at the DRAM at the time that the clock changes state. Unfortunately, with DDR5, it became clear that before it reached end-of-life speeds, that eye was going to collapse. And so it was no longer possible to get away without having some sort of equalization on the input. However, because of the nature of the DRAM process, there still is no room and no power for traditional CDR. PLLs are very expensive, very power hungry in a DRAM technology, and they had to be avoided at all costs. So, as is normal, every piece of complexity possible is moved back to the controller in order to keep the DRAMs as simple as possible and be compatible with their processes. And of course, there are a lot more memories in a system, DRAM devices, than there are controller devices, so this makes economic sense. What it also means, though, is that you have to be able to understand and deal with these concepts of equalization and dealing with closed eyes. With the adoption of an equalizer for DDR5, this required its own kind of a change to the way the specification is written. Traditionally, all DRAM specs have been written in terms of signals that you can probe and observe at the balls of the DRAM. But for DDR5, because the equalizer inherently lives inside the die, the specification also had to be written in terms of signals that are inside the die. This is quite a big departure from the traditional DRAM specification. And in itself is required a significant change in thinking about how one goes about design and test. Part of the capabilities that needed to be added to things like test and measurement and design tools is to be able to deal with things that happen inside the die that you have to be able to control and observe. So you're looking at a signal, say at the DRAM ball. There's going to be a channel that it goes through that has an impulse response and an equalizer that has to correct for that impulse response. And then out of that, you need to look virtually, either in the design environment, or with real-time signals at what's coming out of that equalizer. These are capabilities that in some form existed for high-speed serial interfaces, but needed to be extended and optimized and customized for the requirements of DDR5. In general, everything is becoming more and more like RF and microwave designs that traditionally have only been probable with antennas or signals inside a circuit. So when looking forward to what might happen after DDR5, is this pace of change going to really continue? And I think the only answer is that it is. With the abandonment, potentially, of NRZ signaling that will be necessary to move into the doubling of DDR5 speeds, you have to start thinking about things the way RF and microwave designers do and data communications engineers do, and that's in terms of the Shannon capacity of the channel. So for example, with LPDDR4, if you look at the spec, it actually utilizes only about 10% of the theoretical capacity of the channel. That's an enormous amount of headroom for a technology to be able to improve and increase the data rates without necessarily exploding the power budget. And the kinds of tools that understand those data communications concepts are going to become increasingly important. So hopefully I've been able to give you some sort of context and background on how the industry got to where it is with DDR5 and where it might be going, and the kinds of concepts that you need to be prepared to understand and utilize in your design and test environment.
Hi there everybody, my name's Stephen Slater. I'm a Signal Integrity and Power Integrity Product Manager at Keysight Technologies. I'm very excited today. I've got Ben Dannon with me. Hi there, Ben.
Hi, Stephen. Thanks for having me.
Yeah, no problem. Ben is a Keysight certified expert and also the proud recipient of a DesignCon Best Paper of the Year award for 2020. And Ben, I see you've got your home gym and home office set up with some interesting things. What are you working on at the moment?
Well, a typical engineer, I don't have to leave. I can work out and then do work. But what I got going on behind me is I'm working on a new TDR application with Picotest. They're coming out with a new differential TDR. So what you see back there is some TDR measurements I'm playing around with.
Awesome. Yeah, great. Thank you. And I'm very pleased you're going to take us through now your rigorous design approach using Memory Designer for one of your DDR4 designs. Before I did that, before we jump to it, I was wondering if I could present some context for what you're going to show. So if you could maybe move to the next slide for me. So what we're going to be looking at is Memory Designer, and in a nutshell, it's a complete workflow for your next generation memory design. So you're going to be showing people the system level simulation, part of it in the bottom left corner. We heard in an earlier presentation about DDR5 and the need for equalization. So Memory Designer uses IBIS model, IBIS AMI models, and built-in receiver models to be able to apply equalization, open up the eye, find the most optimal taps. We've got SI Pro for the electromagnetic extraction, and there's a DDR setup wizard to help generate the best known method for ports and frequency plan and things like that. And then we also have VIA Designer for pre-layout design study of VIAs for DDR. So what you're looking at there is some command address VIAs where it's like a multi-drop. So overall, this workflow gives you a fast and productive way to connect your wires together. We've got different solver technologies like statistical and bit by bit. You can even generate IBIS AMI models from inside Memory Designer, and it connects through to compliance test software, Keysight's compliance test, DDR4 and LPDDR4 applications. So with that kind of context setting, I'd like to pass over to you, Ben, and maybe you could take us through your design.
Thanks, Stephen. Happy to. Okay, so this is a design that we recently finished all the simulation work on here at Northrop Grumman. This design involves a custom ASIC, a custom package that's sitting inside of a socket model. And for those of you that don't know what we do here at Northrop Grumman in the Maryland area, we do complex systems for electronic warfare, or EW, air-based systems, land, and sea. And so what we're showing you here today is how we did a multi-board simulation model for a DDR4 2400 application. Okay, let's get into the design assumptions. What I want to show you here are basically how we set up our overall system model. Everything was done at room temp. Nothing from a power integrity side is included in these. However, that's something we can talk about later if that's important. There isn't any DFE or equalization that's enabled, and for the simulation setup, random jitter is included. In fact, up to 2%. In all cases I'll show you here today, 2% jitter is what you'll see injected at either the memory controller or on the SD-RAM, depending on whether it's a read or write. All the simulations were done in ADS using their Memory Designer tool, and all the extractions were done in SI Pro. The simulations I'm showing you for the eye diagram results that are generated here today are all statistical. However, in the slides that are available in the resources, you can see bit-by-bit simulations as well as analysis done for other nets such as CAC and up to 4 byte lanes running. The IBIS corners that we're looking at here today are just for the max setting. And all the simulation models that we extracted from SI Pro include all the crosstalk across both byte lanes. Let's move into quickly the models. So for the IBIS model, it's a custom cadence ASIC. And here I'm just showing you the header of that custom cadence ASIC model that we use. And what I want to also emphasize is at the bottom right of the slide, you're going to see this little indicator move around in the presentation. But there's a red box that's around the memory controller. And that's just to emphasize where we're focusing within the system model. So moving on to the socket model here, what we got from the vendor were really only 3 models, right? So we're using an ironwood socket. And so these are the 3 models that we got available from the ironwood socket. And so these are the respective differential or single-ended insertion and return loss. I'll show you the MCM model here in just a second. Combine the MCM and the socket model, those are what make up our total package model. So what we have is a custom cadence die that's sitting on an MCM or a multi-chip module that we design, and that's a substrate that sits inside of a socket that's mounted to our circuit card assembly or PCB. Moving on to the DIMM connector or the DIMM slot. This is what we get from Amphenol. So it's a regularly available off-the-shelf DIMM connector from Amphenol. There's the part number. There are 2 models you get from Amphenol in this currently available model, and those I'll show you later in the slides how we set those up to do a multi-byte lane simulation. All right, now let's look at the UDIMM. So the UDIMM is a JEDEC approved format, and so this is what you can get and download from the JEDEC website. You can see the micron part number there, and the JEDEC format that we're using is a UDIMM RCD1 format. So what you see on the left is the SI Pro imported model, and then I'm just pointing at the stack up that was used with this imported model within ADS.
Hey Ben, there's other ways to model DIMMs as well. Is there a reason that you chose to extract an EM model of the DIMM?
Yeah, and so the main reason for that is crosstalk, right? So typically what's available from a lot of these memory solution providers like Micron and Samsung and others are EBD files for the DIMM design. Those are great. However, they don't include all the crosstalk. So if you're doing a multi-byte lane simulation with an EBD file, it's not the same as an EM extracted model, which you can easily get with SI Pro.
Thank you.
All right, so let's move on quickly to the Micron SDRAM IBIS model. This is the IBIS model that's available from Micron's website with the DIMM, the part number I called out before, and you can see that's just the MPN that we're using within the IBIS model. All right, exciting stuff. Let's get to the analysis, right? So what everyone's here to see. Here I'm showing you the DDR4 2400 results for 2 byte lanes, including both data mask and the 2 strobes. We'll start with the write, and then I'll quickly go into the read. Before we get to that, let's go into a quick recap of the system model, right? So this is everything that was done to set up a memory designer simulation for a multi-board simulation model. So you could see from the left to right, we have the IBIS model for the memory controller, the Cadence SoC. Then we have a combined MCM and ironwood socket. That's our package model block. And then we have an EM extracted model from SI Pro for our circuit board that we designed, right? Our printed circuit board here at Northrop. And then we show you how we built the DIMM connector model in just a minute from using models from Amphenol. That flows right into a DIMM model that we extracted in SI Pro into the 2 IBIS models from Micron.
Hey Ben, I was wondering, this is a very impressive system that you've set up, but you do have experience with ADS from prior work that you've done. How long would you say you've spent with Memory Designer so far?
Less than a year.
Okay.
And to be honest, Memory Designer was so easy for me to get up and running. I only had to watch one video on YouTube available from one of your colleagues, Vandana, and it was a great video. I watched that. It was very easy and intuitive for me to set up a Memory Designer model for the very first time. To be honest, the way I feel about Memory Designer, you don't have to be an expert in memory design to run a memory design simulation. So memory design architectures are quite daunting, right? There's a lot of complexity, a lot of nets. Memory Designer makes that very easy for you.
Awesome. Yeah, thank you. I'm very pleased to hear it. Thank you.
So let's get into the MCM and socket model, how we built that, right? So you're seeing basically one long block on the left there. There are ports on the far left, right? And then you have multiple blocks on the right going to other ports, right? So from left to right, that's kind of how we're reading this, right? So on the very left, the big long block there, that is the MCM extracted model from SI Pro. So SI Pro is actually able to take in an entire MCM, and we're using 15 nanometer technology for this MCM. And so you can see that that is the extracted model that we pull right there into the schematic, and we connect that and wire it up to the available blocks from the vendor from Ironwood. And that's unfortunately, if this was one complete model extracted from SI Pro, it would be very easy for us to just do this in a block. But you get what you get with vendors, right? So unfortunately, you sometimes need to have that flexibility to be able to wire these up like this. And with ADS, you still have that flexibility. Okay, let's go into the DIMM connector, right? So the DIMM connector, this is how we took the two different models from Amphenol and wired up for the 2 byte lanes, right? So all 16 DQ lines, 2 data mask, and 2 strobes. Now let's quickly go into how we set up the UDIMM-EM extraction and how we set that model up. So what you see at the top left is a view from SI Pro, kind of focusing on the area of where all the nets are of interest. And then I'm showing you on the right a top and bottom view of the entire model. And you can see all the via structures and parasitics are included in this model. Also of importance to note, I've turned off all the layers so you can see those structures a bit more clearly. And the 15 ohm resistors are included in this model. You see how those are wired up there in that block underneath the top block. All right, getting into some results, right? So again, to recap, this is for an IRIS corner setting equal to max, and we're injecting 2% random jitter at the memory controller. Looking at the eyes, you see a total of 20 eyes, right? That makes sense. We're looking at 2 byte lanes, so there are 16 DQ signals, 2 data masks, and 2 strobes. And we have a data mask that is per the JEDEC standard, right? And a bit error contour. And then, so that bit error contour is a calculated result based on the statistical simulation. And if we hadn't injected any jitter, we would have expected that contour to rest flush along the edge of the eye. But because we've injected jitter, we can see that that contour popping off the eye as we see here in front of us. Yeah. An important thing to note here is that as long as that contour doesn't violate the mask, we're looking at the worst case analysis where the probe point is depicted in the bottom right at the SDRAM ball.
Yeah, I was just going to add the point that the eye is treated as a megabit eye. So in other words, the contour would be exactly the same at 1e to the 6. But obviously, because you've added random jitter and it's got a statistical profile, then we get to see that how close the eye would be at a really low bit error rate like 1e to the minus 16. So yeah, that's great.
All right, now let's flip to a DDR4 read cycle. So to do this, it was actually pretty easy. All we had to do was tell the controller that we're doing a read cycle versus a write cycle, and then update a couple settings in each respective IVIS model. Set your ODTs and make sure those are set appropriately on the memory controller side now. As you see, we're setting an ODT of 48 on the controller side, and then you can see the result, right? So naturally, we expect the eyes to look a little different, right? We have a different transmitter on the SDRAM side from Micron than we do on the memory controller side from the Cadence model, right? So, but you can see all the eyes are nice, big, wide, and open, and we're looking right there at the die bump, right? So that's where we're probing. And so we can say with confidence that based on this multi-board simulation model with all the crosstalk that we've included, we are not going to have an issue with any of these signals that we're looking at.
Now, but in the detailed work that you did, where you also looked at the command address bus, there were some kind of insights that were taken away. So maybe could you elaborate a little on that? What did the analysis allow you to understand from the design?
Yeah, I think the biggest challenge with the command address nets, especially with a multi-board simulation model, is that with a DIMM, your command address nets, the reference is not the traditional VSS or ground. It's your VDD, right? We've got to go back to our electromagnetics 101 lessons where a plane is a plane, right? So the return current is going to flow in the nearest plane of the least impedance. And so setting your ports appropriately for that is the quick solution to mitigate getting a bad model. So that's the key.
Awesome, thank you.
Well, thanks, Stephen, for letting me share our work here at Northrop Grumman. Really appreciate it. It was a pleasure.
Yeah, no, thank you very much, Ben. And I think it's truly a pleasure to have you, and thank you for sharing this detail with us. And for everybody watching today, then you can actually download the full PDF that includes many more slides than what we've included here, covering all of the work that you did. So, hey, thank you for joining us, Ben. It's excellent, and talk to you. It's time now to take a look at Memory Designer in action. Let's take a quick look at what some of the brand new features in Memory Designer for 2022 are. Firstly, we can now create IBIS AMI models that cover LPDDR5 as well as DDR5. We can support GDDR6 and the latest GDDR7 that includes PAM4. We can also support HBM2E and 3, and we have a brand new faster DDR analysis in SI Pro, which uses the same DDR wizard as before. To put things in perspective, though, we need to make sure that we're capturing the design team's challenge, which is we're trying a brand new design at next-gen speeds. This design's going to need to be higher performance than ever before, but also high reliability, and that has the design team concerned about things like crosstalk, jitter, the new equalization methods, and new eye masks. A very typical design cycle starts off first with pathfinding, trying to find the best topology. Then laying out the board and going through a post-layout verification, then prototyping and testing the board, and finally debugging. The challenge, though, is at that point we now need to iterate back around, and it can take 3 to 6 months to get to a pass design. What Memory Designer aims to do is to reduce this, get through to first pass success, and do it in 1 month or less. We're going to take a look now at an LPDDR5 design where we have DFE turned on. You can see on the left-hand side the signal as it exits the transmitter. Then it goes through the channel, which happens to be a pre-layout channel. And then you can see what the eye would look like if we didn't have any equalization turned on. So we do have an open eye, we do have some margin, but clearly the eye is not as open as when we turn on the equalization. And we see we have 1-tap DFE. We can actually quantify how much more open the eye is, and we can see down here in the table that we have 40% greater eye opening due to having the DFE turned on. Back in the schematic now, you might be wondering where the LPDDR5 model actually came from. Well, we generated it with our IBIS AMI model generator, which is built into Memory Designer. I'm going to get started by opening up an existing model that we've created before. So just browse to the existing folder so I can bring it up. And then you see that first we have an electrical delay that we can add. We could put in VREF calibration into the model. CTLE is actually a very cool one because we have the ability to specify the different poles and zeros, but most important of all is you can actually plot them so you can see what the response looks like. And then we've got automatic gain control, compression, and DFE. And in DFE, you add in the resolution of the taps, as many taps as you want, whether it's to be adapted or not. And then we come to clocking. Now, clocking is one of the most interesting parts of the model and something that we do very special in Memory Designer. We can actually take in 2 input waveforms into the model so that you can clock the DFE at exactly the right moment, which will handle jitter as well as equalization at the right time. It's easy now just to press the build button and we will see that our model has been created. And then you might ask, where is the model actually being consumed? So we apply it in this DRAM memory model. So I'm clicking in and you see that you specify the IBIS AMI model. And then now we go into some of the parameters. So here you could go and select a different model, a different type of setting for each of the DQ, or we can set them up as a group as we've done here. So applying all the settings as a model group. Now, as the model selector itself, there's a few different analog models that we can choose, and I've chosen a variable called ODTs to be set, which gives me the ability to sweep this particular value. So I go into the Memory Designer setup under the Batch Sim Setup tab, and you can see that it's found my variable ODTs, and then in the value list I have the ability to add additional models from that IBIS file. And then I just press the Generate Batch Sim Setup, and it creates the Batch Sim controller, and that is pretty much all I need. I can now press Simulate, and it will run through this simulation 3 times, covering those 3 different models that I wanted to sweep. Let's continue the tour by looking at the smart bus wire. If I double click on it, you'll see that it's not just a single connection, but it's connecting many signal IDs together with the Auto Connect button trying to pair the unique values together. Next, I can click on this Smart Memory probe, and that can give me access to all of the signals that are available in these components. I select the ones I care about, and then I select which particular measurements I want to see for that group or for individual signals. Now, since we set up those multiple ODT settings, we could go to Design Exploration now, and we could click on the receiver. So we just want to look at the eye height and width of the receiver, and we can set our own special settings for what would be a pass and fail condition, which would typically be tougher than what you might choose for the JEDEC standard. Then I give it the name of the Excel file where I want the results to go, and then it's just a matter of hitting the Simulate button. As soon as the simulation is finished, we get an Excel report that shows us the pass or fail for those 3 different ODT values for each of the DQs, which I can go through and find out if there's any passing or failing conditions. In this case, though, looking at the eye diagrams, they're all wide open, but clearly one is better than the rest. Okay, so let's turn our attention now to moving into post-layout verification. So first thing we're going to need is a PCB. So drop down the PCB Smart component, and then double click into it, and you see it says what you want to browse to, S-parameter data or an SI Pro generated cell. So let's move over into SI Pro, and here's one of those giant boards from earlier. You see it's got 8 memory channels, and so I'm just going to filter the nets here. I'm going to look for channel 0, and then maybe we'll take a look at the first byte lane of data nets. Okay, so then I'm going to select the first byte lane, right click and rapid scan them. And rapid scan now is breaking down those individual signal traces into their constituent elements. And it gives me the result, and what I'm going to do is change the reference impedance, kind of the target impedance, to be 40 ohm, which is what it's designed for. And you see that the longest section of the traces are all nearly 41 ohms, and if I click on one of them, it shows me the individual segment pieces. Next thing to check is if I select all of them, it will show me the electrical skew between each of those signals in the group. This was a great design. There was only 6 picosecond skew amongst the whole byte lane. We can visualize the impedance within the geometry like this, and then if I launch the DDR setup wizard, now we're well on our way to setting up our first SI Pro EM extraction. So to make things easy, we just select the memory controller, and then we go and select the where the DRAM would connect in. So this is the DIMM connector on this board. And SI Pro is now calculating all of the nets between those 4 components that are DDR signals. And then it processes them into DQ, DQS, command address, and etc. And then it's as simple as pressing the new Generate DDR Analysis button to generate the new faster DDR analysis. And once you run the simulation, then you're going to get a range of different options, but the most important is Generate Sub-Circuit, which gets us back into our schematic. In conclusion of the demo, let's summarize the key takeaways. So number 1, you've seen that we have support for many next-gen memory standards. Number 2, IBIS AMI model generation for LPDDR5 and DDR5. It's feature rich, it's easy to use. You don't need to worry about not having access to vendor models. You can start pathfinding today. Our simulators and models utilize the most accurate forward clocking behaviors we demonstrated, and the complete workflow covers everything that you might need to do in your design workflow. Then we come to finally EM extraction. SI Pro now has a much newer, faster DDR analysis, and setting it up is really simple. Well, I hope you enjoyed the demos. Next steps, where to find out more information. You could go to Keysight University. It's on keysight.com. There you'll find an SI Fundamentals course. You get a certificate at the end. You could also visit the HSD homepage. I've got the link there. That's where you can research more about the products you've seen here today. But most important of all is just to get started with a self-paced workshop. It covers Memory Designer as well as SI Pro. All you need to do is simply fill in your survey results and let us know in the free text field that you're interested. Okay, on to question and answer time. Let me take a look. Some of the common themes I see is questions about forwarded clocking, saying that, yeah, I understand that the Memory Designer supports forwarded clocking, but what happens if the model from the vendor doesn't support it? Hey, that's no problem at all. If you've got a model that just has like an imaginary CDR inside it, even though the DRAM wouldn't, that's okay. We can consume that model inside of Memory Designer. But keep in mind, you'll always be the most accurate treatment of jitter and the application of the right timing instant for the DFE if you're able to input 2 waveforms into the model. So if you don't have access to a model that can handle that, you can generate such a model very easily from inside of Memory Designer. Okay, looking at next questions. What happens if you don't use Keysight for the EM extraction? Will that break the Memory Designer flow? No, that's not the case at all. You can bring in S parameter data from any EM vendor tool, and what we do is we even read the S parameter header text to try to find the port names so that we can help parse them and try to connect up signal IDs in an easiest possible way. It will always be smoothest if you are using SI Pro with Memory Designer, just by nature of the cohesive flow that we've created. But yeah, you're not limited to only using SI Pro. Okay, and then we've got a question here about high performance computing, HPC. It was mentioned in the very first presentation, but we didn't hear much more about it. How is it licensed? Yeah, so we don't license by cores. So, multi-threading is something that is just part of our standard simulators. But we do require licenses for parallel jobs. So it's a really simple scheme. If I want 4 jobs in parallel, then I'll need my SI Pro simulation license, and then I'll need to add 3 HPC EM1 packs. And those HPC EM1 packs can be used for any EM simulator type, so we can reuse them for PI Pro, power integrity simulation as well, to speed up those. Okay, I think that's about time, so I'm going to pass back to our moderator, and thank you for your time today.
Okay, it looks like that's all the time we have for questions today. Thank you so much, Stephen. Thank you again for attending the PathWave Design 2022 launch event webinar. And if you're a current user, be sure to sign up for the Keysight ADS users group on LinkedIn. The copyright of this presentation material is owned by Keysight Technology. I'm Anna McCowan, and thank you for joining us. Have a great day.